Alright, so I've started recording. Practice quiz is up. Okay, I told the worker to work on the other end of the house, so shouldn't have quite so much pounding now, just faint pounding. Well, that's kind of heavy pounding. Yeah, I'm right underneath you, right over here. Yeah, it's this whole room. The thing is right here. The computer's right here. Alright, I just told him to go way to the other end of the house. Alright, so average velocities, we're gonna, since we need it at 3, we're gonna need the input here at 3, and then we're gonna need some stuff very close to 3. 3.01 maybe, and then 3.001. And then we'll look at these intervals. So if I put 3 in, I'm going to get 9 times 3, 27 minus 2, which is 25. If I put 3.01 in, hang on a second. Squared times 3 minus 2. And then so my slope between 3 and 3.01 is going to give me one estimate, and when I give him the slope between 3 and 3.001, it'll give an even better estimate. So I can see which direction I'm going to go into. Should I make it even smaller than the smallest interval, or make it larger? And when I do the slope, I take the difference in the y coordinates, which is 0.1803, divided by the difference in the x coordinates, and that's 0.01. It moves the decimal 2 places to the right. When I do this one, I subtract this minus this, 20, and that's going to give me the difference of 0.018003, and then this 3.001 minus 3, which is 0.001. This moves a decimal in the numerator to the right 3 places, 1, 2, 3. Hold on. Yeah, 1, 2, 3, so it's 18.003. And so my estimate the instantaneous velocity, I'm going to guess that the instantaneous velocity is 18 exactly, since they're getting quite smaller as we're moving down here. And so we've done a fair amount of these lately, but it's a really kind of a foundational type problem, so I just want to double check on this. Are you okay with this one, with where you had to kind of come up with all your points on this? And again, we could have used 2.99 and 3. It could have been on either side. Everybody good with this? Give me a little bit of feedback on, in the Discord chat channel. Alright, and let's come back and do these first couple of limits problems. This is more similar to the homework. And the homework, there's stuff I need to be grading, and I'll be grading it starting this weekend. I'll get caught up with the grading this weekend. I kind of got behind on that because of grading the test for this week. Okay, anybody still need more time on 2A? If not, then let me go ahead with that. All right, the first thing I'm going to do is state the form. The form is when I plug in 2, I get 4 plus 2, 6, minus 6, 0 over 0. And then what that tells me is I can't figure this out until I do some algebra. Or I could find this limit with a table or with a graph. But those would only give me approximate answers. The only way I'm going to get my exact answer is if I can do it algebraically. So I'm going to rewrite it. This in its factored form. Do the signs next. These two numbers have to multiply to be a negative, so we need one positive, one negative. And I want 3 and 2 and the larger one positive, so that the middle term is positive. Okay, and then once I have them factored, these can reduce. And then I get the limit as x approaches 2 of, I just plug it in. And 2 plus 3 turns out to be 5. And that's my answer. Alright, now go to B. Work on that one. Alright, so on 2B, a classic student mistake is to launch right into this. X plus 6 all over x minus 4, and then say, oh, nothing cancels, so I'm not sure what to do, and get disoriented. Alright, the mistake that was made that I just did was neglecting to do the form first. This needs to be the first step every time, and it's a huge time saver, because in this case you're going to get 16 minus 36, which is negative 20 over 0, and when the form is a over 0, we immediately know the answer. The answer is does not exist. This limit doesn't exist. As x gets really, really close to 4, this denominator gets so incredibly small and we get huge fractions, and it doesn't exist. So I put this problem in to really reinforce the importance of doing the form first, and then you won't get disoriented with, oh, things didn't cancel, all that stuff. Alright, now my copy and paste thing, as I was putting these problems in, kept calling all of these A. So they're all back to A. Do the next A one. And this OneNote kind of works much like Microsoft Word, except it wouldn't let me change these A's back to B's, so it doesn't have quite the functionality of Microsoft Word. Alright, anybody need more time with this one? Just let me know. Alright, we're good to go. And we start with the form. Plugging in 2, I get 4 minus 4, which is 0 over 0. And then I'm going to get the limit as x approaches 2. Factor this out. To multiply two numbers to get negative must be one positive, one negative. 2 and 1, I want the larger one negative, so that I get the negative middle term. Now, these two are similar, but they need to be exactly identical to be able to reduce. To get them to be exactly identical, we are going to have to... I like the one in the top. I'm going to leave that the same. I'm used to x coming first. To get the x to come first on the bottom, I just factor out a -1. And then x becomes positive and the 2 becomes negative. And then these can reduce. Notice, right before the reduction, if I substitute 2 in, I'm going to get 0 over 0. But as soon as I reduce, it's not going to be the case anymore. Now, I can substitute the 2 in, and I'm going to get 3 over -1, so the total answer is going to be -3. Alright. Give me a little feedback on this one. Need more practice, or totally good with this one? This one there, starting to get a little bit tricky. Alright. Okay. So, next one. The next A. Go ahead and work on that. Alright, anybody need more time here? Alright, so let's go with form. Substitute 0, I'm going to get 1 minus 1, which is 0, over 0. It's the only, it's called the indeterminate form. It's the only form that we can't instantly tell what the answer is. But this is the only one, the only kind of limit that we're going to be interested in. And when we do the slope, the instantaneous slope, which is the main concept of calculus, it's going to involve this kind of limit. And so this is a hugely important type of problem for us. So we are going to do limit h approaches 0. Alright, so what I'm going to do is the same trick I showed you yesterday. If I want to get the square root to go away, by the way, that square root goes over the h. If I want to get the square root to go away in the numerator, the only way I can really do that if it's 2 terms is multiply by what's called the conjugate. Because I'm going to get middle terms when I FOIL these two out. And the only way that the middle terms will cancel out is if one's positive and one's negative. If they're identical, but one positive, one negative. Okay. Now I don't multiply out the bottom part. I want to leave that, but the top part I want to multiply out. When I multiply out the top part, this times this, the square roots go away. This times this is plus one of these. And then this times this is minus one of those. And then this times this finally is minus 1. Okay. Now, what happens? These two kill each other out. And this plus 1 and this minus 1 kill each other off. And all I'm left with is the limit h approaches 0 of h on the top. And see why I didn't multiply out the bottom? Because I need the bottom factored out so I can cancel. This, in the original problem, this h was, when you plug it in, that's going to give you the 0 in the 0 over 0 form. And I need that h to cancel. So I don't want to multiply it out. I want to have it factored out so that it can cancel. And that becomes a 1. Divide by h, and these become 1s. And then, now, as soon as you've canceled out the h, it's no longer 0 over 0 form. Plugging in the 0 now, I'll get a 1 on the top. 1 plus 0 is 1. Square root of 1 is 1. 1 plus 1 is 2. There I go. 1/2. Alright. Give me feedback on this one. Good to go? Really need more practice? Pretty okay, but need a little more practice? Anything in between? Let me know where you're at with those. Okay. Alright, so this particular kind of problem is going to need some individual prepping for some people, for sure. And you might need to do some similar ones. And I can just, circulate a little bit more practice in as time goes on that. And then let's go to the last one of these limit ones. I'll give you a little time to work that one out. All right, anybody still need more time? All right, then let's go ahead. So I'm going to get well, first of all, I should never forget this, the form. My substitute -4, I'm going to get 0 on the top and 0 on the bottom. So then I'm going to, from here, I'm going to say that the least common denominator of the two fractions in the top of in the numerator, the least common denominator is 4 times x. So this one needs a 4. I'll multiply the bottom by 4, multiply the top by 4. This one needs an x. I'm going to multiply top and bottom by x. So I'm going to get the limit as x approaches -4. Now some students really get tired of writing limit as x approaches -4 and writing this over and over each time that they do this. And if you want to, some people say let cap L equal, and then they write this expression. And then they just put a cap L in front of each one. And so there are ways to kind of shortcut this if you need to. All right. So we're going to get, now these two fractions in the numerator both have the same denominator of 4x. So you can add the numerators. X plus 4 over 4x divided by 4 plus x. I'm going to make that one over 1. And then that's equal to the limit as x approaches -4. And copy dot flip. The top one stays. The bottom one flips. And I'm going to rewrite that as x plus 4 to make it look identical to the other one. And then these are going to reduce. And I am going to get, as x approaches -4, the top is 1, the bottom is -16. Okay. A little bit of feedback on this one. Was this tougher than the previous one? How to relate, and so on. These are two of the tougher ones with the limits. Algebraic reduction, but sometimes the algebra, it's a little complex. All right. All right, so let's go to number 3. It says, without using a calculator, state what the sequence goes towards. For instance, if I had a sequence of 0.9, 0.99, 0.999, so on, I would say, that's getting closer and closer to 1. It gets infinitely close to 1. All right. Now, don't use a calculator, don't punch these into anything, just use your intuition. What do these fractions, as a, figure out what kind of result you're going to get for each of these fractions. What is this sequence going towards, and what is this sequence going towards? Let me give you a minute. Okay, anybody need more time? Okay, let's look at these. So this 7 divided by 1/10 is really asking how many times bigger is 7 than 1/10. And you have to, or in other words, how many times do I add 1/10 to itself to get to 7? And for the adding 1/10 to itself 10 times, I get to 1. And then I have to do it 7 times, so that's 70. And this is going to be 700, 7,000. What's this sequence going towards? As this gets smaller and smaller, this gets larger and larger without bound. So we say it's going towards infinity. And what's happening with these? As now notice the top number is getting bigger each time. And so is the bottom number. But the bottom number is getting bigger by a lot. It's getting bigger a lot faster than the top number. The top number very slowly is getting larger. But the bottom number is really getting larger fast. So you're getting in decimal form, this would be something like 0.5, 0.06, 0.007. And what's happening is this whole thing is getting, when the denominator is getting faster, a lot faster than the numerator, it sends the whole thing to 0. If these were negative numbers on top, it wouldn't make much difference. They'd all be negative, but still driving it smaller and smaller to 0 from below the x-axis. And here it's coming to 0. So it really wouldn't make much difference whether these were negatives or positives. All right. So this concept in number 3 is real foundational to what we're going to be doing today. So give me a little feedback on this. Does this seem, coming back to you, real clear with this on number 3, or is it a bit fuzzy? Okay. All right. So let's go to questions on the homework now. Now, one question that was stated earlier was 71, I believe. Yeah. And any other questions? So if there's something before 71, I could do that first. 37 and 38. And this is all in 2.3. All right, let's go here. Let's look at 18 first. And this is page 80. So and let me insert some extra space here. All right, so this is saying, suppose the limit as x approaches 2 of f of x and the limit as x approaches 2 of h of x are both equal to 5. Now, let me visualize that. there's two different numbers that we have here, a 2 and a 5. Where does the 2 go on the x or the y-axis, and where does the 5 go? Well, the 2 is easier to decide, because x approaches 2, that's got to be along the x-axis. And then the 5 is the output, f of x, or g of x, as the limit go to 5, so since that's an output, it's got to be up here. Now, where the 2 and the 5 intersect is right here. We know that the function f and the function h are such, we don't know how they come to this point. Maybe f comes like this. Now, if it did it like this, and then maybe h is coming like this. Is that the way that they're coming into it, if this is true? Well, if this is true, yes. Somebody chiming in?
Is h of x looks to be the largest of, so all the h of x values should be larger than f of x?
That's right. This inequality is saying that the h of x is greater than or equal to both the g of x and the f of x. So I have these backwards. This one can't be the f, it's got to be the h. And this one would be the f. Okay. Now, it must be true that for all values of x, so this h that's above top, it might actually go something like this and then loop back up. And this one might go through here and loop back down. Because for all values of x, the h is up above the f. Okay. Now, the g, for all values of x, is stuck in between. It's higher than the f and lower down than the h. So the g must be somewhere in between these two dudes. All right, now find this limit. Well, as x gets really close to 2, g is squeezed in between f and h, but f and h doesn't have much room to squeeze between them right there because they're both going to 5. So this thing must also be 5. So if we can visualize this, we can get it. In fact, this one is, there's a theorem called the squeeze theorem. And that theorem, let me point it out to you. And yeah, it's on page 77. So let's go over here. Squeeze theorem. And I'm going to even copy it and paste it here. Oops. Let's come back here. Oh, should have it. Should be just the squeeze theorem. Oh, okay. Maybe it was doing it right all along. And let's give myself some more space. All right, so Squeeze theorem in general says that if some function is stuck in between two other functions for all values of x, then if the two extremes have a limit of some number, then the one in between must have that limit at that same number. So this is kind of generalizing this case right up here. And the squeeze theorem is used sometimes in cases like this, where you might have a function, like if you were taking the f of x equals cosine x, let me get it here. Over x squared. All right. If I had a function like this, now I could tell that as x gets really, really large, this fraction is going to get smaller and smaller and smaller. And normally I would say that this function is going to go to 0 as x gets really large. But the problem with the cosine on the top is that the cosine oscillates between -1 and 1. So it isn't always decreasing, sometimes it's increasing from -1 to 1. Sometimes it's decreasing back from 1 down to 0 to -1. And so this numerator function can oscillate back and forth while the denominator keeps getting larger and larger, driving the whole fraction towards 0. What we wind up doing with that function is we compare it to 1 over x squared and -1 over x squared. This function, how does it relate to this one? Well, the f of x is always bigger than or equal to this one, because this is the worst case scenario where cosine x, the smallest it can ever be, is -1. This is the best case scenario where the largest cosine x can ever be is +1. And this one, if you take its limit, it goes to 0. This one, its limit goes to 0. So if that's, and then this one is always squeezed in between these two. So this one must also go to 0. And so it can handle some, strange cases like that with the squeeze theorem. And it's, I want to point out at this point that there's going to continue to be problems like this, where it will be advantageous to you if you're not a big reader and you don't tend to read the textbook each time. You probably want to at least skim through the textbook and kind of, see that what are some of the main headers and what are some of the big ideas, and when you're on this page of the textbook, it's kind of, you can see it's a fairly, it's got a header, it's got, some paragraphs dedicated to this squeeze theorem, and you might not really understand it, but by just looking at it briefly looking through the textbook before doing the homework, you might realize sometime later that, I couldn't do this one problem, but it might relate to this portion of the textbook that I remember reading something vaguely familiar to that, and then you kind of know where to go back and look. Some of the stuff that you're going to be doing in the calculus class, and it'll get more so as we go on along, if you keep going to calculus 2 and calculus 3, is you'll wind up having to read more stuff to get all the parts of the homework. So that was number 18, and then let's go numbers 37 and 38. Um, and page 80. Alright, so I'm going to prefer, these two are rather similar, so I'm going to do the one that's odd. So leaving an even numbered for you, so that might be one that I can check. So this. All right, the first step is here, we're going to do the form. When I substitute b, I'm going to get b minus b, which is 0 to the 50th, and then these are going to cancel out, and I'm just going to get 0 over 0. And then I need algebra to do this. And I'm going to take the limit, x approaches b, and in the bottom I'm going to put x minus b, with parentheses around it. The top, x minus b. The theme is x minus b. So this one, I would like to have x minus b. But I have negative x plus b, which is exactly the same thing as x minus b, except both terms are opposite sign. So I'm going to do that same trick of factoring out a negative 1. So I can factor out a negative 1 a couple ways. I can do plus negative 1 times, or I can just put subtract parentheses. And if I do that, then I have to change the sign of both of these terms in there. The negative x becomes positive x, plus b becomes negative b. Every time I factor out, I can immediately check my work. If I distributed this minus sign to both, it would give me negative x, it would match this. Negative of negative b, which would match this. Alright, so now I have everything with x minus b's. I cannot be canceling like this x minus b and this x minus b. That would be kind of like 2 plus 3 divided by 3, trying to cancel those 3's. You can't do that. But if I had 2 times 3 over 3, I could cancel. So I'm going to take this limit as x approaches b. I'm going to say what's common to these two terms on the top. X minus b. What's going to be left over from this first term is going to be x minus b 1 power less to the 49th minus, and if I factor out x minus b from here, I get a 1. Again, I could, if I distributed this x minus b to here, I'd recover this one. So I'm checking my work. If I distributed this to this, I'd recover this. All over x minus b. Alright, now, in whatever is in parentheses, we can always think of as one item. So now it's one item times one item. It's more like this, where we could cancel. So now we can reduce, and then once I've reduced, now I can substitute the b for the x, and I'm going to get 0 to the 49th, which is 0. 0 minus 1 is negative 1. Any questions on 37? Alright, that takes care of that. Then I think there's one other one, 71. Let's look at that. Explain why or why not. Determine whether the following statements are true and give an explanation or a counter example. Alright, so I'm going to show you the first one to make sure that you're oriented with this one. And then we'll do a few of these together while I have you work in your groups. So the very first one, it says, if the limit as x approaches a of f of x is equal to L. Now, I understand things a lot better if I can draw a picture. So on A, I might get this little picture here. Where do I put A? Well, x is getting closer to that, so it's got to be on the x-axis. Where do I put L? Well, that's the value of the output, so that must be over here on the y-axis. My function f is going through, I think, this point right here. But it doesn't tell me how it goes through. Maybe it's going through like this. Who knows? And now, it says if the limit as x approaches a of f of x equal to L, which means that as I get closer and closer to a from either side, I have to be getting closer and closer to this height of L. And that certainly appears to be the case. If I squeeze in here, I get squeezed in up there. So if that's true, then must it be true that f of a is equal to L? Well, at first I might think this is true, but in actuality it is not true. Remember, the limit doesn't care what happens at that point. At that point itself, we might have had an open circle. And my thing thinks I'm trying to do something different. Every time I make a small figure, I have to make it a little bit bigger. Might have an open circle here, and it might have it filled in elsewhere. That could be what's happening. And then the limit would still be L, because what happens at your destination doesn't matter. When you have a limit, you're not allowed to reach the goal. You're just saying what happens as we get infinitely close to it. So this one turns out to be false. And you'd have to have an explanation. The explanation be you could have what's called a hole discontinuity. And then the limit would still be there, but f of a would not equal L. F of a could be this other height way up here instead. Any questions on 71A? Okay. So if that's the case with A, let me have you all do 71B. And you might just quickly check in with each other in your groups and say, I think it's false and why or whatever. And then I'm going to pick on one of the groups and see how you're doing, what answer you got for part B. And we'll go through a few of these. Oh, and before you get going on that too, the leader of each group, make sure you have designated somebody to be the spokesman for the group today, and we'll have the spokesman be a rotating spokesman. So for any given day, there's a new spokesman. Okay, group 2. What do you have for B? Anybody in group 2 today?
Well, I wasn't sure who our spokesperson was. So we have it as false because as the limit approaches, as f of x, as x approaches a, the limit of f of x, it's only if you have, if f of x as x approaches a is equal to L, then you know that both one-sided limits are also that limit, but it can't be the other way around.
Gotcha. Gotcha. And what might the graph look like?
So it could be, for example, you could have like a discontinuity or one of like the step ones that we were doing the other day, where
Yes.
on one side it's approaching one f of x, and then as it's coming from the right, it could be approaching a different f of x.
Kind of like that.
Yeah. Mm-hmm.
All right. All right. Very good. Thank you. And you are, your name again is?
That's Francis.
Francis. Thank you. And, all right. Let's have you all do C now. All right, let me check on group 5. What do you have for part C? Anything for part C from group 5?
Can you? Hello?
Go
Hello?
ahead. Go ahead. Who are you?
Who are you? This is
Mm-hmm.
I have f of a cannot equal g of a, but I don't know. I don't understand how to graph it.
Okay, so you
And
think it's
I
true
have
though,
it's not
right?
true.
Though, right?
What's that?
Do you think it's true or
Do you think
false?
it's true or false?
No, I think it's false.
Why?
Why?
I think f of a can equal g of a because I don't know. I don't know how to graph.
Okay,
Okay,
well, let me help you with
well,
that.
let me help you with that.
Let's go to C.
Let's go to C.
So it can get tricky visualizing these things. Let's go on the first one. A must be on the x-axis, and L must be on the y-axis, and F must be going through this such that as we get closer and closer to A, we get closer and closer to L. But it's possible for us to have something like this. That would still be a case where the limit as x approaches a of f of x is equal to L. Because even though at A the height isn't L, We don't care what happens at the end point, at the destination point for a limit. So this might be a possibility for f. Now, g, let's draw that with a different color. G could be something, it has to go with this, but G could also have an open circle. And its height at that point could be something different. And then, here is G of A over here, while here is F of A over here. And so they're not equal in height, and so this one is false as well. Okay. And that's as much as I'm going to do for number 71. But that'll give you kind of a good heading into the rest of that. And we are now at break time, so let's start again at 12:48, 15 minutes from now. See you in a bit. we're going to get started again, and I'm going to use my whiteboard here. So just set this out. And I've unmuted. I think I'm all set. So we are on 2.4, infinite limits. And if I was titling this, if I had been the writer of the book, I would have titled it Vertical Asymptotes Redefined with Limits. Okay, and let's start with a situation like this. If you'll recall from pre-calculus, what I just drew is a vertical asymptote. Suppose this was happening at 2. And suppose, and we know that what happens near 2, near a vertical asymptote, is that typically the graph gets closer and closer to that without touching it. And then, not always, but many of the times, on the other side of it, it goes in the other direction. Sometimes it's coming up on this side too, but more often, it's like this. Okay. This would be a vertical asymptote at x equals 2. In fact, we don't just say vertical asymptote at x equals 2. We say the equation of the vertical asymptote is x equals 2. Because if you have an equation of a y equals something, that's a horizontal line. If the equation of x equals something, that's a vertical line. Now, this isn't really part of the graph, this vertical line, but we use it to help guide us to make the graph accurate. Alright, now, in a situation like this, what is the function? What is a type of function? What would I be writing over here on the right-hand side that would produce this kind of a situation right over here, where the vertical asymptote is here? And anybody can interject here. Does anybody have any idea?
You want a 1 over x, in this case, like maybe like 1 over x minus 2 or negative 1 over x minus 2?
Ah, very good. Either positive 1 or negative 1. And the big important thing is x minus 2 down in the denominator. If you don't have x minus 2 in the denominator, if you don't have a fraction at all, you can't get a vertical asymptote. But if you have something like this in the denominator, now, I like the way you stated, it might be 1, it might be negative 1. Let's try 1 and see if this matches up with this picture right here. So, we'll make a little table. X 1 over x minus 2. And notice I cannot put 2 in. If I put 2 in as an input, I get 1 divided by 0. You can't do that. So not allowed to do that. But let's put 1 in. And when we put 1 in, you'll get 1 over negative 1, which is negative 1. Let's get really close to 2. 1.9. I'll get 1 over negative 0.1, and that's going to be negative, and then we move the decimal point 1 to the right, multiply top and bottom by 10, and we get negative 10. 1.99, 1 divided by negative 0.01, and that's 100 times bigger than that, so it's negative 100. All right, we see that if we had it with a positive, then on the left side of this, 2, we'd be large negative numbers. So we really wanted this to be negative, and if this was negative, then all of these are negatives, and these are positives. And then that would give us this shape over here. And the closer we get to 2, the more that this goes to infinity. And if we made another cycle of function of things, like suppose we were on the other side of 2 at 3. If I plug in 3, I'm going to get negative 1 over 1, which is negative 1. If I plug in 2.1, I'm going to get negative 1 over 0.1, which is negative 10. Okay, so 3, I'm going to be at negative 1. 2.1, I'm at negative 10. This is acting like it should over here. And 2.01 is negative 1 over 0.01, which is negative 100. All right, so we're getting vertical asymptotes. And vertical asymptotes, when you're in pre-calculus, when I teach vertical asymptotes in pre-calculus, I have students memorize this question. Vertical asymptotes asks what input causes the denominator to be 0. And if you asked this question of this function right up here, you'd say, well, the input of 2. And in fact, if you stated it more precisely, you said, when x is equal to 2, then you have the equation of the vertical asymptote. So when you answer this with an equation, x equals 2, you get the equation of the vertical asymptote. Now, this was very much useful to us in pre-calculus. But in calculus, we're going to see that this has limitations. All right. Let me just write something more about this that I had in my notes. As the input gets really close to this illegal input. See, we couldn't put 2 in here. 2 is illegal. We'd get dividing by 0. But as we got really close to it, the fraction gets huge. And this kind of relates to the practice quiz too. Remember on the practice quiz, 7 over 0.1, 7 over 0.01, 7 over 0.001, so on. As we get these things, as the denominators get smaller and smaller, the fraction gets larger and larger. All right. Now, about ready to erase this, so let me take a snapshot. Let's paste that in. Seem to cover up something. I think we're all right though. Okay, now. If I was a student in this class, a concept such as a vertical asymptote would be too abstract for me to relate to. And I would ask, give me an example, like how might I ever see this in real life? So it's going to be a pretty crazy example, but it'll get the point across. Experimental rocket ship. And suppose you have a 1 mile track. Maybe it's a straight line distance instead of a track going around in a circle. And you keep trying your experimental rocket ship out on this 1 mile track. And distance is equal to rate times time. So if we divide both sides by the time, the rate is distance divided by time. And so the distance we know is 1 mile. So we're going to have a little table of time in hours and the rate, which is equal to 1 mile divided by the time, 1 divided by t. And we're going to say, suppose the first time you made this rocket, it was a prototype model, wasn't very good, and it took you 1 hour to go the distance of 1 mile. So then your rate was 1 divided by 1, so you went 1 mile per hour. Now, suppose you tampered with their rocket ship, and you got it to go in 1/10 of an hour, 0.1 hours. Then it did the 1 mile in 0.1 hours, and the top number is 10 times as big as the bottom number, so it's 10 miles per hour. And you tampered with it again. Every time you tamper with it, it becomes 10 times faster. Wouldn't that be nice? And you get 1 divided by 0.01, which is now 100 miles per hour. And you tamper with it again. And as this goes towards 0, what does this go towards? Infinity. And this is what's going to be happening every time, whenever you have an equation where there's a variable in the denominator. That becomes a huge concern for us. We look at variables in denominators and we say, oh my gosh, if the variable is going to cause the denominator to become 0, then the fraction will go off to infinity. And so that becomes, you know, we get radar after a while. Any function that we look at, if it has something in the denominator and if it's just constants in the denominator, we're okay. But if it has an x in the denominator, x minus 6, so f of x is, who knows what it is, but it's got x minus 6 in its denominator, then we know that some really unusual behavior is going to happen as we get close to 6. All right, I think somebody's got their microphone turned on. Let's just check real quick over here. I can hear some extra noise.
It was Josh. He muted it.
Okay, we're all set. Thanks. All right, and so then, now these points where the denominator becomes 0, one of the names in mathematics we give for that is singularity. So singularity points, when the denominator becomes 0, the fraction is undefined. As we get close to it, it blows up. It goes off to infinity. A simple example of this might be if you have 2 electrons. They're going to repel one another. But suppose you push these 2 electrons towards each other. The amount of repelling force is proportional to the distance. The closer they are, the bigger the repelling force between them. Suppose you push these 2 electrons so incredibly close together that it's huge. Suppose you then, what will happen in theory then is you're going to get an infinite amount, you see, because you're going to be dividing by the distance between them. And as that goes to 0, you're going to explode, and perhaps, and some have theorized that perhaps it's as simple as 2 electrons being pushed together, that maybe when they get together and coincide that we get some kind of a black hole there. So all kinds of crazy theories have been come about from looking at the mathematics of these kind of singularities that can happen with dividing by a variable. All right. Any questions so far? All right. Now, yes.
That's dividing by a variable provided that the numerator is a constant because only, or
Good question. The numerator could be anything. And then this function still is going to blow up when x gets close to 6. The only exception to that is, let me show you, is if this factor also shows up in the numerator. So if I have this, then at first glance you say, oh, here's a vertical asymptote at x equals 6. But no, they are going to reduce. And when x is 6.01, you're going to get 0.01 in the top and 0.01 in the bottom. You're going to get 1. This is going to reduce to 1 for every value of x, except for the one value of when x is equal to 6. All right. So it doesn't matter what's in the numerator unless it contains that same factor, and then they would reduce out. And then it appears to be a vertical asymptote, but it was just in disguise. It was really not a vertical asymptote. It canceled out. Glad you brought that up. Any other questions, comments? All right. Now, although the most common occurrence of vertical asymptotes is just having a variable in the denominator, it is not the only occurrence. There are other places where we can have vertical asymptotes. And this is where that definition we learned in pre-calculus is limited. So, for instance, let's take y equals log base 10 of x. If you were to graph this, let me put some real easy values. If x is 10, you're going to have log base 10 of 10. So the question that this is asking is, what's the exponent you place on top of 10 to get a result of 10? Now, we're going to go over, we skipped the review section on logarithms and exponential functions. So if you're super rusty on these, this might not make sense today, but we'll eventually be going over that. But we delayed that section until we do derivatives of exponential and log functions. But I want to mention it briefly right now that this asks the question, what is the exponent I place on top of the 10 to get a result of 10, which is 1. If x is 100, it asks, what is the exponent I place on top of 10 to get a result of 100? I would put a 2 there. If x is 1,000, what is the exponent I place on top of 10 to get 1,000? And I would get 3. If x is 1, you ask 10 to what power is 1? Well, anything to the 0 power is 1. If x is 1/10, 10 to what power is 1/10? Turns out 10 to the negative 1. You bring this down to the bottom, change the exponent to positive to handle a negative exponent. So it's negative 1. If it was 1 over 100, it would be 10 to the what power is 1 over 100. It turns out 10 to the negative 2, because you bring this to the bottom and you get 1 over 100. So this would have to be negative 2. Now, if we take all of these and graph this, so let me screenshot, stick this in. Ooh, it's kind of covering up my stuff. Let me create more space. So I am going to take this function, log function, I'm going to say, well, what would happen if I had a negative value? Suppose I just had negative 1 here. This is asking 10 to what power is negative? And if you raise 10 to a negative exponent, you don't get a negative number, you get a fractional result. If you raise 10 to a positive power, of course you get a positive result as well. This is impossible. Because it's impossible, this does not exist. Now, if we look at all those and we put it into a graph, so when x is 1, our x is going to go all the way out to 1,000 over here. Okay, and when I'm at 1,000, I'm only at a height of 3. And when I'm way back over here, when I'm at 1, I'm going to be at a height of 0. When I'm at 10, I'm at a height of 1. When I'm at 100, I'm at a height of 2. This is a very slowly growing function. And over here, when I'm at 1/10, I'm at -1. When I'm 100th, I'm at -2. It comes and it goes really close to the x-axis without ever touching the x-axis. And what we see is there's a vertical asymptote. This has a vertical asymptote at x equals 0. But there was no fraction and there was no denominator equal to 0 over here. So the vertical asymptotes, if we were to look at them more closely, we would see that our definition that we used in pre-calculus, what inputs cause the denominator to be 0, is not a complete it's not going to get all vertical asymptotes. All right, we're going to look at vertical asymptotes. Again, in the light of limits now. Okay. So, vertical asymptotes in light of limits. And I'm going to start with this question. So, number 1. Can we say the limit as x approaches 5 of 1 over x minus 5 equals infinity? So, is this a reasonable thing to say, to use infinity in this way? And I'm going to have you discuss this in your groups, and I'll ask a group in just a minute if you think the answer is yes or no and why that is the case. All right, so let me give you a minute. Okay, group 4. Does this seem reasonable to say that this is equal to infinity?
I don't think it would reach that point. It would just get infinitely close.
Okay, but you'd say, I like the way you'd said it couldn't reach that. Infinity is something that we can never reach. It's more like getting bigger and bigger without ever having an upper bound on it. It's well put. So if that's the case, if we say we could never actually get there, but we're going there, would this be reasonable then to say this? As long as we said, you can't actually get to infinity. Does that seem reasonable?
Possibly. Like if as long as you're saying that it can't get to that point, it seems sort of reasonable. I'm
Okay.
not too.
And is this Sally that's talking?
Yep.
Okay. Um, and does everybody agree with that?
I was thinking that maybe because from our original definition of a limit that if both one-sided limits convert or have the same limit, then the limit exists. But since on one side it's approaching negative infinity and then coming from the other side,
We have to look at that part. Let's look at this. If we only use numbers like 5.1, we'd be okay. 5.01. The smaller we got, getting closer to 5, the bigger we would get and we'd go off to infinity. Alright, but what Francis is pointing out is that we could also be approaching from the other side. 4.9 and 1 over, and that would be negative 0.1, which would be negative 10. 4.99, 1 over negative 0.01, which is negative 100. So what is happening here is that from the right side it's going up, but from the left side it is going down. So because of that, the answer is no. The two, for a limit, general limit to exist, the left-hand limit and the right-hand limit have to be the same. Since these are different, one's going to positive infinity, one going to negative infinity, we'd have to say this does not make sense. Let's go to number 2. Can we say the limit as x approaches 5 of 1 over x minus 5 squared is equal to infinity? Discuss that in your groups, and I'll pick on a group in a moment. And just check, make sure that everybody knows who the spokesperson for the group is today in your group. All right, group 3. Is this reasonable?
I say it is because your output would always be positive since it's a exponent of 2.
That is correct. So we're always, when you'd get these, since these would then be squared, if this was squared, these would be squared, and it'd always be positive. And so you'd be having going up on both sides like this. So this one is yes. Now, let's give this answer a little bit more completely. But only if we define precisely what we need. All right, I want you to consider this kind of problem. The limit, when you start to use infinity as a number, you can possibly run into really big problems. And Sally was pointing out that we never really get to infinity, but there's even bigger issues than that. Let's look at this. The limit as x approaches infinity of the quantity 2x minus x. Now, according to the limit laws that we know, we should be able to distribute this and make this a limit, two separate limits. And clearly this one is going to infinity. You know, that limit law, you could bring out the 2 in front of it, but even if you don't, you can tell this is going to infinity. This is going to infinity. And infinity minus infinity, anything minus itself is 0. And you should be getting 0. But that's clearly not the case. Because 2x minus x is really x. And as x goes to infinity, this whole thing goes to infinity. And you can get all kinds of strange results when you start to work with infinity, and all kinds of results that don't make sense. And so when, in the history of math, when they tried to start using infinity as a symbol, as like as some other number, a lot of the brightest minds could see that this was going to lead to some very messy situations, and were warning and saying, hey, no, don't ever use infinity like this. In fact, the same controversy happened with 0. There was a long time that 0 wasn't used, that there was no 0. If you went in the Roman trading houses and you traded as a person in Rome, they had these counting boards because, you know, they're trading lots of chicken eggs for lots of other different things, and they had to count up all these things. And in these counting boards, they had these slots. And you'd put the number of items in each one of these slots, and this could be, you could think of this as the ones and the tens and the hundreds and so on. And they would go, and when they didn't have, like, there were no tens, they would just leave that slot empty. And so they could work on everything and get addition and stuff correct by leaving slots empty. But when they wrote it down for a book, they didn't know, like, for the number 2017, there was no 0, and it looked like this. They couldn't distinguish between 2017 and 217, like this. And when it was proposed that the number 0 should become valid, a lot of the brightest minds objected, because they realized that when you have 0, you're going to have problems with division. You can't divide by 0. And then they said, oh, that's going to lead to all kinds of problems, and we shouldn't some of the brightest minds were making arguments like nature abhors a vacuum and we shouldn't use zero. And it turns out that we can use zero, but we just have to be really careful about its use. And we had to make certain fractions illegal. Cannot divide by zero. And similar things happened with infinity. We can use infinity, but we can't use it like we use ordinary numbers. We have to be very precise about what we mean when we start to use infinity, because we could get things where infinity minus infinity doesn't, give us what we think it would, and so on. So let me take a snapshot of this.
Professor, I have a question
Yes.
just for clarification. So when we were learning the forms, like A over 0, which would be the case here if we had, some of these graphs that we've been working on. And so when we were told that the limit does not exist generally for that form, does that mean like when it says it doesn't exist that you don't get an actual value? So can infinity also be justified in that case because it's not an actual value? Is that what it is?
That's
Or?
what we're going to wind up doing today, is for certain answers, instead of saying does not exist, we're going to have another optional answer, which will be infinity or negative infinity. And so we will wind up doing like this one. That limit we would still say does not exist. But this limit, we will say, oh, you can call it infinity. Okay? So we're going to get some answers that now, instead of being doesn't exist, it does exist in this sense where we get infinity. Does that answer your question, Francis?
Yes, yes.
Okay.
Mhm.
All right. Now, let's define it precisely. Definition. We say the limit as x approaches a of f of x equals infinity if the values of f of x can be made larger than any number cap n no matter how large cap n is by taking x sufficiently close to a on either side of a. But not equal to a. Not allowed to set the x equal to a. Okay. All right, with this definition, we could see that the limit as x approaches 5 of 1 over x minus 5 does not exist. As we saw in the graph, if you approach it from one side it goes to infinity, approach it at 5 from the other side it goes to negative infinity. But the limit as x approaches 5 from the positive side of 1 over x minus 5. Now from the positive side would be like 5.1, 5.01. So we'll always get positive numbers here, and then we would say that this result is now infinity. And we could get this fraction. Suppose I wanted this fraction to be larger than 1 million. Then I just make x to be within 1/1,000,000th of 5. So 5 plus 1/1,000,000th would give me 1/1,000,000th in the denominator. The reciprocal of that is 1,000,000. I can get bigger than 1,000,000 by just choosing x to be super close to 5. Any questions? All right. Now let's switch over here. All right. I think I covered up, so I'm going to have to create some more space. And let's go to the textbook. All right, log me out. I think it's page 85. Okay, so let me shrink this up a little bit. All right, so here we are. The definition of the one-sided limit, and it has pictures associated with these. So this limit as x approaches a from the positive is equal to infinity. That means as we're a little bit bigger than a approaching, we go off to infinity. Okay, and the one-sided limit could also be to the negative infinity, looking like this. It's approaching a from the right, we go to negative infinity. All right. And then this new definition of a vertical asymptote. This more general definition doesn't miss anything. Now it says if, as x approaches a of f of x, goes to either positive or negative infinity, or if the one-sided limit goes to either positive or negative infinity, either from the right or from the left, then the line x equal a is called a vertical asymptote of f. So that's how we get vertical asymptotes. All right, now I want to have you make a distinction over here. Which is the format of a vertical asymptote? There were two possible formats. Limit as x approaches a of f of x, or number two, limit as x approaches infinity of f of x. Which of these two formats is the format of a vertical asymptote. So let me give you a moment. Discuss that in your group. And I'll pick on a group in a minute. All right, group 6. Which format? 1 or 2?
Would it be the first one?
You're saying this is a vertical asymptote. If so, what kind of thing would go on the right-hand side? Is that Christian?
Yeah, sorry. So what thing would go on the right-hand side?
Yeah. What kind of answer would go on the right-hand side if this was a vertical asymptote?
If there's a vertical asymptote, then it'd be like 1, or at least the denominator would be, it would somehow equal 0 in order to create that if you plugged in A.
All right, so I'm not asking what the function's going to be, just
Oh,
what
okay.
the limit's going to be. The
Oh,
limit.
okay. It's a vertical asymptote, and it should be. Wait, sorry.
Let me help you out here. This is kind of a theoretical question here, so I can see why you're struggling. It could be either positive or negative infinity. And it'll show up over here. This is the correct answer. You were right. It's
Okay.
the first one. And if it's a vertical asymptote, you might get negative infinity or positive infinity showing up. And the picture would look like this. A would be somewhere along here, and then you're going to have a vertical asymptote. And as x approached A, now this one, it didn't say plus or minus, so it has to be from both sides, going down to negative infinity. And then this is a vertical asymptote. All right. If you had something like this, let me point out that this, in contrast, suppose this was equal to 2. This is not a vertical asymptote. This instead would be, anybody want to chime in on that?
Horizontal asymptote.
This is a horizontal, because the output is now 2. And as x gets super, super large, the function is getting closer and closer to 2. Now this is going to be the focus of the next section that we look at. It is horizontal asymptotes. But vertical asymptotes, it's like this. All right. And notice where we were at here. This had x approaching A, and the infinity or negative infinity shows up on the right-hand side of the equation. And underneath the limit, there's no infinity. But for horizontal asymptotes, we're going to get into the following section. The infinity shows up down here. There's no infinity over here. It just is down below the limit. Okay. And let me take a screenshot of this. Insert a bunch of space. And all right, we for the last thing here, a tiny bit more space. We're just about out of time here. All right. Last thing, sketch the graph of an example of a function that satisfies these conditions. And number 6, since we hardly have any time here, let me just do it myself real quick. As x approaches 0 from the right, my function goes off to infinity. That's what this first condition says. As x approaches 0 from the left, my function goes off to negative infinity. As x approaches infinity, the function goes to a height of 1. That's a horizontal asymptote. As x goes to infinity, this is going to get closer and closer to this line. As x goes to negative infinity, the function is going to get closer and closer to that line of, oh no, not negative 1, to positive 1. So, sorry about that. This should be coming up like this. Alright, so the homework is, I think this is 2.4 that we're on today. And we'll stop here. Anybody have any questions? All right, have a great weekend. And I need
So, Robert,
yes.
just wanted to let you know that I missed class today